just a reminder of the fundamental theorem of calculus and then some examples. So, reminder. So the fundamental theorem of calculus, part 1, it says that if big f of x is the integral from any number a until x of f of t dt, then if you do the derivative of this big function, it will give you just f of x. You plug in x into the function. Okay, and the second part, and both of them, of course, we proved last class, that the antiderivative or the area from a to b under the curve of f of t dt is equal to the antiderivative at b minus the antiderivative at a. Okay, so these are the two parts of the fundamental theorem of calculus. Let's do a few examples. So example 1. Let big F of x equals the area from 3 to x of sine of t squared dt. Okay, so find big F prime of x. Okay, so what's it going to be? So I'm doing the derivative of the integral from 3 to x. It says you just plug in the x into the function. So I just have to plug in the x into the t. And so that's very, very simple. So big F prime of x is just sine of x2. Finished. Right? F of x, f of t. Instead of t, I put an x. Instead of t, I put an x. Okay? So that's why I said it was very easy. Once you get the theorem, it's simple. So let's say another example. Let's
Sir, we can't hear you. I personally can.
Yeah, I can't hear you either.
Okay.
okay. So let's say f of x is, let's say, -1 until x squared, okay, of e power t3 dt. Find f prime of x. Okay, so can you guess what this is going to be? Right? I just plug in the x2 inside the t. Okay, so it becomes e power x2 power 3, so that's x6. You understand this?
Yeah.
Okay, but I'm missing something.
Sir, I have a question.
Yeah,
So what happens to the 3 and the -1 on the bottoms?
nothing. Okay,
Nothing?
so that's a good point. So as you see, my theorem tells me that it's completely independent of the a.
Okay.
Okay, just f of x, plug in the x here. If it was x2, you plug in x2. Okay, the only thing is that since this is a derivative, and this, if instead of putting in x, I put a function, then I would have to do the chain rule. So I have to do times the derivative of the bound. So x2 prime.
Do you mind repeating that again? When do you have to do the chain rule?
Okay, so if this is x, you plug in x. If this is x2, then you have to plug in x2 times x2 prime. You have to, because it's the derivative.
Okay.
this becomes a chain rule. It's a function of a function, right? If it's f of a function now here. So the derivative, you would have to do a chain rule here next to derivative of x2. You understand this?
Yeah.
So this is e power x6 times this will be now 2x.
So you just squared the t to the 3?
I just
Is that what you
replaced
did?
t. I replaced the t by x2. So x power 2 power 3 is x power 6.
Okay.
Okay, let's do another one.
Sir,
Yeah.
could you just explain what we're doing? We're deriving what's inside, and then we're replacing the variable with the top thing.
You're not deriving what's inside. You're replacing the variable inside. Okay, that's what it is here. But since this is a function, well, I have to derive with respect to this function as well, because there's a chain rule involved. Here there was no problem because, of course, I plugged in x and it's like multiplied by x prime, okay, which is 1. That's why we don't write it. But here it's not x anymore, it's x2. So I have to derive it. There's an impact here. It's 2x. Is it clear or not? You want to repeat?
Yes, please.
Okay, so again, so I'll do it step by step. Okay, let's go. Let's do it here step by step. So let's go like this. Let's say u of x is equal to x2. Okay, so basically, or yeah, okay, so basically, f of x is equal to f, in this case, is f of u of x. That's what we have here. Okay, so here I could put u of x here. And so if I derive this, f prime of u of x, we know using the chain rule that this is equal to f prime of u times u prime. Right? Chain rule. So that's why this u prime, this is my 2x. It's a function of a function.
I see. Thank you.
Okay, so basically this will be, if you want, f prime of u is just, this is just f of u. Okay, just f of u times u prime. That's what I have here. Okay, another example. So from 0 until sine x2, we want dx, basically the derivative with respect to x, of square root of 1 minus t squared. Okay, so basically, we're looking for the derivative. So I'm going to plug in the function inside of the t. So this will be square root of 1 minus sine squared of x2 times the derivative of this. Which is, so 1 minus sine squared is cos squared square root is cos. So this is cos of x2. The derivative of sine of x2 is cos of x2. Is that good? I missing something here?
Yeah, the 2x.
I'm missing a 2x, okay? Don't forget the chain rule again. Okay, so there's two chain rules here. Derivative of sine x2 and then the derivative of x2. Okay, and so my answer here will be 2x cos squared x2.
Sure, so we always derive the thing we add, right? Not the equation
We always derive what? I'm sorry?
like we always derive what's above, like the sine x2. We don't derive the equation, like the
Oh,
base
no,
equation.
the inside, no. It's always f of x. You plug in this inside.
Okay.
Sir, why the 2x?
The 2x is from the derivative of the x2,
Okay.
right? It's chain rule here. Okay, let's do another one. So let's say you have something like this now. Derivative with respect to x. And now let's say we have from x to x cubed. Okay, so there's an x on the bottom now of anything, I don't know, 2 power t2. Okay, so now I have a function on the bottom as well. Okay, so let's just remember that this is actually an area. It's an area between x and x3. Okay, so what I could do is I could say that this is d dx of, and I could express this area as the area from 0 to x3 of 2 2 power t2 dt minus the area from 0 to x 2 power t2 dt. Do you understand what I just wrote here?
Is that like using a second thing of calculus? You would subtract.
Well, it's just understanding that this is an area. Okay, so if I have the area, let me just make a little picture here. So I have the area like this, the function, and I'm looking for the area from x to x cubed, right? I'm looking for this area. Okay, well, I could say it's the area from 0 to x3 minus the area from 0 to x. It would give me, so that's what I did here. From 0 to x3 minus from 0 to x. That will give me from x to x. Is that okay?
Sir, why do we put the dx in front of the integral?
Why do I
Is
put
it like,
this?
yeah.
Because I'm looking for the derivative of this integral.
Oh, okay.
It's like writing f, big F of x equals this, and I'm looking for f prime. Simple.
So you're looking for the derivative of an integral, so basically the normal function itself?
Yeah. Yeah. So now I have two situations like above. It's easy. Okay, of course I put 0 here. I could have taken any number here, right? This number is irrelevant. So what is this? Can you tell me? You should know how to do this one now. The derivative of this is 2 power
X plus 6.
x6 times
3x power 2.
3x2 minus, and here, what is it?
2x power 2.
2x power 2, finished. And that's my answer. Okay, so basically, it ends up, this I showed the step, but it ends up putting x3 in here times the derivative of x3 minus putting x here times the derivative of x. Okay, try one more. And after that, that's pretty much all there is to say about the first part.
Sir, do you mind just explaining why we like the step above that? Like why do we subtract two things?
Why do we what? I'm sorry?
Why do we subtract um like
This
the
here,
yeah.
this,
Mhm.
because I'm looking for this area here. Okay, and this area is what? It's the area from 0 to x3, 0 to x3, minus this area here, which is from 0 to x. If I minus these two, I'm going to get this.
Okay, yeah, I get it.
Understand?
Yeah.
Okay, so let's do hopefully the last one. You're going to get it. If not, I'll do more. But dx of, let's say, um, x sine x until x2 of 1 over square root of 1 minus t3 dt. So 1 over 1 minus x6 minus, you plug in the x sine x in here, 1 over square root 1 minus x sine x cubed times, don't forget the derivative of, oh, I forgot here to multiply actually, by 2x. And here I have to multiply by the derivative, which is a product rule. So sine x plus x cos x. So dx, so let's say x2 until 5 of tangent of t2 dt. Okay, so now the x on the bottom. So if I am to do it like we did before, I could go like this: dx of what, and I will separate it. I will do from 0 to 5 of tan t2 dt minus from 0 to x2. Okay, just like we did before when we decomposed the area. Okay, and this is an area from 0 to 5, so that's a number. And so the derivative of this will be 0. Okay, I'm going to write this down. dx 0 to 5 tan t2 dt minus ddx 0 to x2 tan t2. Okay, and this is 0. Understand that this is 0?
Yes.
Okay, because there's no variable here. You're going to find the area under this curve from 0 to 5. That's going to be a number. It's going to be 20. I don't know. And so I just have to do this one. And so basically, it ends up being the same thing as 5 to x2, but with a minus. Okay, that's what it means. So I plug in x2 here, tangent x4 times 2x, and I'm done.
Do we not put the minus in front?
Yeah, sorry, I forgot the minus. Let's now use the second part of the fundamental theorem of calculus to evaluate this. The area, the integral, right, from 0 until pi over 2. So the area of, let's say, sine cubed x cos x dx. Okay, so let me do the first one, and you'll do one right after. So remember, part 2, so now we're looking for the area from 0 to pi over 2 of this function here. So if I were to do Riemann sums here, it wouldn't work. Okay, you would end up with sine cubed of, I don't know, pi over 2i over n, right? Pi over 2n, pi I over 2n. It's complicated, okay?
Here it's pi over 2, right? Not...
Pi over 2 here, yes. Okay. Or you can see on top, I guess. Just put it a bit lower. So I'm going to use the fundamental theorem of calculus, which tells me I have to find the antiderivative of this, okay, and plug in pi over 2 and plug in 0 and minus them. The only thing is that I have to do a substitution here. Okay, so let's do my substitution. U is, of course, sine x, right? I have to do an antiderivative here. And du is cos x dx. So what do I have here? Antiderivative, right? The area. So u cubed times du, right? This one, it's a simple substitution. The only thing now is that I have to change the bounds. That's important because here I'm stating that x goes from 0 to pi over 2, but here it's the u that changes. So let me see, what's u? So I'm going to write here that I'm dealing with the bounds. Okay, so I know that u is sine of x. That's my substitution. So if x is 0, right? If x is 0, what's u? Well, u is sine of 0, right? U is sine of 0, which is 0. So start at 0. Okay with this? But if x is pi over 2.
Sorry?
Yeah.
Could you repeat again how you got x equals 0 is u equals sine 0 equals 0?
Yeah, because the bounds here, okay, on top, tell me that x is between 0 and pi over 2. This is the area that I'm finding, between 0 and pi over 2 for the x. But now I'm not dealing with x anymore. I'm dealing with u. So I want to know u is from what to what. You get it?
Yeah, I get it.
So what I'm doing is I'm using what's the relation between x and u? And I know that u is sine x. That was my substitution. That's what allows me to transform the integral from here to here. So u is sine x is my transformation. So let's see, okay, when x is 0, what's u? Well, plug in x is 0 here. You get u equals 0.
Okay, so
yeah, sorry.
So there you found the minimum?
Yeah, the minimum value
yeah.
for u, exactly.
Okay.
Okay, and if x is pi over 2, which is my upper bound for x, then u will be sine of pi over 2, which is 1. And so goes from 0 to 1.
You okay with this?
Sir, do you mind explaining the bounds thing? I don't get it.
Okay. Bounds again. I'm interested in finding what is the smallest possible value for you and the maximum for you. Smallest and biggest for you. Okay. I don't know. I don't know what u is bounded by, but I do know that u is sine x. That I know. And I know that x is bounded between 0 and pi over 2. That I know. Is that clear? Did I go too fast?
No, it's good.
Okay, so again, so I know that u is sine x, and the smallest value of x is 0, so the smallest value of u will be sine of 0. I know that u is sine x, and the highest possible value of x is pi over 2, so the highest possible value of u will be sine of pi over 2, which is 1. So that's why u goes from 0 to 1. Okay? And at this point, I'm going to use the fundamental theorem of calculus and find the antiderivative now. So the antiderivative of u3 is u4 over 4. And you evaluate it from 0 to 1. That's how you write it. Okay, so the antiderivative is u4 over 4. And then you write from 0 to 1. These are the values of u. Okay, and that is equal to, so you plug in 1. So 1 power 4 over 4 minus, you plug in 0, 0 over 4. 0 power 4 over 4. And so my answer is a quarter. Okay, so the area between 0 and pi over 2 under this function is exactly a quarter. That's what it says. Another example here. So the antiderivative, let's say from 1 to 2 of, I don't know, x 5 dx. Okay, it's a very, very easy one. Okay, no substitution to do nothing. Direct antiderivative, which is what? Can you tell me? X6 over 6 evaluated from 1 to 2. So you plug in 2 here, 2 power 6 over 6 minus you plug in 1 here, 1 power 6 over 6. And that's the answer. 2 power 6, I don't know what that is that 64? I think it's 64. 64 minus 1 is 63 over 6. That's your answer. Okay, much, much faster than using the Riemann sum, which would be a real pain here. Integral, let's see, from 0 to pi over 3 tangent x dx. Fix it. Write a bit more. So it was until pi over 3. Okay, that works. Tangent x dx. So we have to do a substitution here. 0 pi over 3. So the tangent x is equal to sine x over cos x dx. And then we you remember, we did u is equal to cos du negative sine x dx. Sine x dx is negative du equals integral of, so it will be 1 over u times sine x dx, which is negative d. Okay? So the only thing missing now, of course, is the bounds. Okay, so don't skip the bounds. If you skip the bounds on the test, you will lose points. Okay, I need to see that you change the bounds here. So bounds, my substitution is u equals cos x. So let's say if x is, my lower bound is 0, then u is the cosine of 0, which is 1. And if x is pi over 3, then u is the cosine of pi over 3, which is 1 half. 1 until 1 half. Okay, so you might find this weird that this is higher than this one. True, because it's an area, but we'll talk about this when we do the properties of the definite integral. Okay, so what do we get here? If I plug in, if I do the antiderivative of this, I will get ln. So I have negative ln absolute value of u evaluated from 1 until 1 half. Plug in the half here, so negative ln of 1 half minus negative ln of 1. Okay, and this is, so ln of 1 is 0, ln of 1 half is negative ln 2, so this will be just ln of 2. That's the answer here. Okay, so you notice that there is no plus c here. Like in the indefinite integral, there was a plus c. In the definite integral, there's no plus c anymore. We're not finding a general antiderivative of the function. We are finding an actual area. This is the actual area, it's a number. Okay, so the answer to a definite integral is a number. It's not a function.